SwayamPrabha. Digital India. Educated India.
In the last lecture, we have seen the steering requirement when the automobile takes a turn. That means the front two wheels must be rotated appropriately to prevent the tendency of side slip, and we have also seen how the Davis steering gear achieves it. We noted that the Davis steering gear is a 6-link mechanism with 4 revolute and 3 prismatic pairs. It is due to the prismatic pairs the Davis steering gear is costly and also more difficult to maintain. Today we shall discuss a simpler version of this steering mechanism known as Ackermann steering mechanism. As you shall see, this Ackermann steering mechanism is a simple 4R linkage. This is the Ackermann steering linkage, which, as we see, the short axle is mounted on the body of the automobile. This is the body. Similarly, this short axle is mounted on the body of the automobile. And these two short axles are connected by a coupler. So this is O2, A, B, O4. So O2 A, B, O4 is a 4R planar linkage. This is the top view of the automobile. Here are the two front wheels and the back wheels will be here. Now this is also a symmetric linkage in the sense this link length is same as this link length and this angle is same as this angle. While the car is going along a straight path, these two angles must be same because it has to be symmetric, because the car may take a right hand turn or a left hand turn and these two turns must be identical. So this linkage O2 AB O4 is a symmetrical 4R linkage. because it is simpler, we have to also pay a price, in the sense that the perfect steering condition cannot be maintained for all radius of curvature of the turns. The perfect steering condition can be met only at certain points, and we hope, if it is properly designed, that for other radius of curvature, the tendency of slight slip will not be too much. So what we see, that this 4R linkage has 4 link lengths. Say L1 is the fixed link length, which is given, that is decided by the location of these two pivots, O2 and O4, on the body of the automobile. Then L3 is the coupler length, which we have to find out, and L2 is same as L4, and we have to also determine this link length for a proper steering action. We shall synthesize this 4R mechanism and explain the synthesis procedure by a example, and we shall use what we have discussed earlier as Freudenstein's method, that is the analytical method of linkage synthesis. Let us discuss the design of an Ackermann steering mechanism with reference to this particular example. In this car, the wheelbase, that is the distance from the rear axle to the front axle, is 3 meters. If you remember, this wheelbase we denoted by B. And the distance between these two fixed pivots on the body of the automobile is 1.8 meters, which is called P. It is said that the minimum radius of curvature for this center point G of the body of the automobile is 10 meters. That means the minimum value of R, if I call that R min, for this center point G is desired to be 10 meters. The car has to obviously take a right hand turn, a clockwise, or a left hand turn, or counterclockwise. So as we see, the radius of curvature for this point G can go from minus 10 meter to minus infinity, or plus 10 meter to plus infinity. When the car goes along a straight path, the point G goes along a straight line, the radius of curvature is infinite. Now, as we noticed that the rotation of these two wheels must be correlated for perfect steering condition given by the following equation. Say, cot of theta 6 minus cot of theta 2 is to be P by B, where theta 6 was the rotation of this outer wheel and theta 2 is the rotation of this inner wheel. This is what we derived while we discussed the heavy steering gear. But in this case, let me call the rotation of this outer wheel, I am considering a turn in this direction, the outer wheel, so I call it, instead of theta 6, let me call it theta 4. So the rotation of these two wheels, theta 2 for this wheel, theta 4 for that wheel, has to always maintain this relationship. But such a function generation obviously is not possible for all values of the radius, that means for all values of theta 2 and theta 4, if we use a simple 4R linkage. We can maintain this condition only for some specific values of theta 2 and theta 4, not for the entire range. We call this fixed pivot O2, this point A, this point B, and this point O4. The rotation of O2A we represent by theta 2 and rotation of O4B we represent by theta 4. Now we know that we can have 3 accuracy point synthesis, that these 3 pairs of values of theta 2 and theta 4 can be satisfied by a 4R linkage. However, in this case we must have a symmetric linkage, that means this O4B, the link length L4, and O2A, the link length L2 must be same to maintain the symmetry, that is identical terms for the clockwise or counterclockwise. So L2 is same as L4. Because this has to be satisfied, we do not have a choice. Obviously, we cannot even go for 3-point synthesis, we can go only for a 2-point synthesis. O2, O4, this is the fixed link length L1, AB, that is the coupler link length, is L3. So what we see, we have to determine what is L2 and L4 and what is L3. Where L1 is given to be 1.8 meter. The fixed point O2, A, B and O4. Because we can go for 2-point synthesis, we decide that one of the accuracy points corresponds to the state configuration. And in the state configuration, the linkage has to be symmetrical, that is, this angle must be equal to this angle. If you remember the Davis steering gear, this angle, which we called alpha at that time, turned out to be half of cot inverse P by B. Here P is 1.8 meter and B is 3 meter. So this is half of cot inverse 0.6, which is equal to approximately 73 degrees. That is for the Davis steering gear. For P equal to 1.8 meter, B equal to 3 meter, this angle, which we call alpha then, turned out to be half of cot inverse P by B, approximately 73 degrees. For this problem, we assume these two angles to be 70 degrees. Quite close to 73 degrees, I take this angle as 70 degrees. This angle is also 70 degrees. This is L1, this is L3, and O2A and AB are same, which is say L2. This length is L2, this length is also L2. Now the radius of curvature for the point G, as we have noted already, goes from minus 10 meter to minus infinity and plus 10 meter to plus infinity. And we have only one accuracy point to solve for, because we have already taken this as one of the accuracy points, and there are only two link length ratios, namely L1 by L2 and L1 by L3. So we can satisfy at the most only two accuracy points. One of the accuracy points corresponds to the state configuration. That leaves us only with one further accuracy point. Of course, the symmetry of the linkage ensures that I need to consider only one kind of turn, say from 10 meter to the straight path. Minimum 10 meter radius for G and straight path for G, because the negative part, that is the other direction of the turn, will be automatically satisfied. Now the question is, which radius I should try to satisfy the steering requirement. For that, we go back to our Chebyshev accuracy point. Let me now complete this problem of designing this Ackermann steering linkage represented by a 4R linkage O2, A, B, O4 to satisfy the steering requirements. The symmetric linkage ensures that the right hand and left hand turns are taken identically. So one accuracy point, I consider this straight path when these angles are same. This angle is also 70 degrees. We have already chosen theta 2 equal to 70 degrees and the corresponding theta 4 which we measure from the line O2, O4 is 180 minus 70 degrees is 110 degrees. So this is one pair of coordinated movement that has to be satisfied by this polar linkage. Symmetric linkage takes care of the right hand and left hand turn identically. So we are left with only one more accuracy point. Let me take it as Rg, for which value of the radius of curvature of this center point G I must satisfy the requirement. And let us say the wheels have to rotate for that value of Rg. This I call Rg. The question is, what value of Rg this requirement, the steering requirement, that is all the perpendicular to the wheel axis intersect at one point. This is the perfect steering condition. So what is this rotation and what is this rotation? This I will call, say, delta theta 2 and this I will call delta theta 4. To find the accuracy point, that is the value of Rg for which the perfect steering action will be satisfied, we proceed as follows. We see that the curvature, which is defined as 1 upon r, goes from minus 0.1 meter inverse to 0.1 meter inverse, right? 10 meter radius of curvature means 0.1 meter inverse curvature. This is called curvature. So we can take three accuracy points in this range, minus 1 to 0.1, as follows. We draw chi, this is say 0, this is minus 0.1, this is plus 0.1. Then we draw a regular hexagon. We draw this regular hexagon within this circle, semicircle, which we have done earlier, and these are the accuracy points. This is 0.1, this is minus 0.1, and this is 0. So, if I call it chi 3, which is same as minus chi 1, so chi 3 is, this will be (0.1) into 1 minus cosine of 30 degree. This angle is 30 degree. Radius is 0.1, this is 30 degree, so this is 0.1 into cosine 30 degree. Which is 0.0866 meter inverse. The corresponding Rg is 1 upon chi 3, which is 11.55 meters. This is one accuracy point, and the other accuracy point will give you Rg is minus 11.55 meters, and other is Rg is chi 0, so Rg is infinity. That is the straight path. Now, straight path we have already satisfied by this pair of coordinated movements. these two pair of values of theta 2 and theta 4. Similarly, for 11.55, if we do, minus 11.55 will be automatically satisfied because the linkage is symmetric. So now we can apply Freudenstein's method to solve for the link length ratio. This RG will take 11.55 meters. So this was given to us as 1.8 meters. So if I call this point I and this point say C, this point D and this point E, we see we are taking IG, the radius of curvature of the path of the center point is 11.55 meters. And this wheel base was given to us as seamed. So this is 1.5 meters. If the wheel rotates by delta theta 2, previously it was vertical, this line was horizontal, so the rotation is, this is same as delta theta 2, and rotation of that wheel is this much, which is delta theta 4. So we can see tan of delta theta 4 is 3 meters. This OPD is 3 meters divided by ID, which is IC plus CD. And CD is 0.9 meter. And IC I can get from IG and CG. CG is 1.5 meter. So this is 3 divided by square root of 11.55 squared. IG is 11.55 squared minus CD squared, that is 1.5 whole squared, that is IC, and CG is 0.9. So if you calculate this, you will get delta theta 4 will be 13.65 degrees. Exactly the same way I can calculate delta theta 2, because tan delta theta 2, that is the rotation of the inner wheel, is O2E by IE. O2E is 3 meters by IE, that is IC minus CE. And IC we have already got here, so it is 3 divided by square root of 11.55 squared minus 1.5 squared minus 0.9. If you calculate this, you will get delta theta 2 is 15.87 degrees. So we see that if we want to satisfy the perfect shearing condition corresponding to the radius of curvature of this point G for 11.55 meter, that is a little higher than the minimum value of 10 meters. This is our accuracy point where the shearing condition will be perfectly satisfied. that these two wheels from this neutral position or the state position will rotate by delta theta 2 and delta theta 4, which are given by 13.65 and 15.87 degrees. So we get a second pair of coordinated values for theta 2 and theta 4. Theta 2, this we call it second value, which is 70 degree minus, this is 70 degree and it is rotated this way by 15.87 degrees. So 87 degrees. So that gives me 56.13 degrees. And theta 4 2, similarly we get 110 minus 13.65 degrees, which gives me 0.35 and 14, that is 96.35. This is not 56, this is 54, sorry. This is 54 degree. 70 degree minus 15.87 degree is 54.13 degree. And the corresponding value of theta 4 is 96.35 degree. So we get two pairs of coordinated movements, the two pairs of values of theta 2 and theta 4, which must be satisfied by this 4-bar linkage O2, AB, O4. So we write the coordinate equation, cosine theta 2 minus theta 4 is K1 cosine theta 4 minus K2 cosine theta 2 plus Kc. Where K1, K2, K3 are the three design parameters, where K1 is L1 by L2, K2 is L1 by L4, and K3 is L1 squared plus L2 squared minus L3 squared plus L4 squared divided by twice L2, L4. Now we know K1 is same as K2 because L2 is same as L4. So this I can write K1 cos theta 4 minus K1 cos theta 2 plus Kc. Now this equation, cosine of theta 2 minus theta 4, K1, if I take common, I can write it as K1 cosine theta 4 minus cosine theta 2 plus K3. And these two pairs of movements have to be satisfied by this equation. So if we substitute, we get two equations to solve for K1 and K3. If we write these two equations, if I substitute here, I am getting cosine 40 degree is K1 cosine 110 degree minus cosine 70 degree plus Kc. And if I use this set of values, then I am getting cosine 0.22 and 642, 954, 42, 42.22 degree is K1 cosine theta 4 is 96.35 minus 54.13 plus 6. So from these two equations I can easily solve for two unknowns, namely K1 and K3. If we solve for K1 and K3, by solving we will get K1 equal to 1.953 and K3 is 2.102. So L1 is given to us, L1 is 0204, which is 1.8 meter. So from here I get L2, which is same as L4, is equal to 0.9217 meter. K3 I can use to solve for L3, but I can also use this configuration where I can see that L1 is L3 plus 2L2 cosine 70 degree. L2 cosine 70 degree plus L4, which is same as L2, this is also 70 degree, so again L2 cosine 70 degree plus L3 is L1. I can either solve it from this value of K3, because I know already L1 and L2, L4, I can find L3, or I can directly use that and use L1 and L2, which I have obtained, to find the value of L3, which will turn out to be 1.17. So, and L1 was given to us 1.8 meters. So we can use the Prudence method to solve for this, to synthesize this Ackermann shearing mechanism to satisfy the requirement that at a particular value of the turning radius for the center point G, which we took as 11.55 meters, the shearing condition will be exactly satisfied. It will be exactly satisfied for an identical left-hand turn. This we did for right-hand turn, and obviously it is all right for the straight path. But for all other values of the radius of curvature of the path, this shearing condition will not be exactly satisfied. So this is a much simpler mechanism than Davis gear, but it is obviously not satisfying the shearing requirement for all values of the turning radius. It is satisfying only for a particular value of the turning radius, and for all other radius we are almost ensured that the deviation is not much. This intersection of these three lines will not be too far off, such that the tendency of side slip is not too much. That is where we finish our discussion on shearing mechanism, and next we shall discuss another special class of mechanism which we call universal joint or Hooke's joint. Now we shall discuss another type of special mechanism which is also used in automobile, which is known as universal joint or Hooke's joint. If you notice, you will find that the output from the gearbox of an automobile is taken by a propeller shaft which connects to the differential, and this propeller shaft and the differential input shaft are connected by a joint which is known as universal joint or Hooke's joint. Actually, this is used to connect two intersecting shafts, to transmit power between two intersecting shafts. The axis of two shafts, if they are intersecting at a point, then the power can be transmitted from one shaft to another by what is known as a Hooke's joint. First, let us have a look at the physical construction of such a Hooke's joint. This is how the physical construction of a Hooke's joint looks like. This is one shaft, say the input shaft, and this is the output shaft. These two shafts are intersecting at this point. Then these two shafts can be connected by this mechanism which is called an universal joint or Hooke's joint. As we see, this fork, this is called a fork, this fork is integral with this input shaft. Similarly, this fork is also integral to this output shaft. And this is a cross arm. The angles between these two parts of this cross are 90 degrees. This is vertical, this is horizontal at this configuration. This horizontal part of this crossbar is mounted in two bearings in this fork. Similarly, the vertical part of this fork, arm is mounted in these two bearings carried by this fork. This is how and now if this shaft rotates, this cross arm also rotates and it will be able to transmit power to this shaft. This is what is known as universal joint or hook joint. In the next figure, we will show what is the kinematic representation of this mechanism. We should note that there is a revolute pair here. The shaft is rotating with respect to the frame or foundation. This is link number 1, this is link number 2, and there is a revolute pair. And the axis of the revolute pair is this. Similarly, there is a revolute pair here. This is link number 1, and this fork or the shaft is link number 4, and there is a revolute pair. And the axis of the revolute pair is along the axis of the shaft, and these two revolute pair axes is intersecting at this point. There are two revolute pairs here, there are the two bearings, and kinematically they are one revolute pair because the axis of these two revolute pairs is same, and they are connecting the same two members. This cross arm, which I can give link number 3, between 2 and 3 there are two bearings, but kinematically there is only one revolute pair because the axis of both these bearings is same. Similarly, there is a revolute pair here between 3 and 4. This fork or the shaft is link number 4 and this is link number 3, and there is a revolute pair, and the axis of this revolute pair is also passing through this point. So all the revolute pair axes are intersecting at this point O. So there are 4 revolute pairs kinematically, one here, one there, and one here, one there, and all the 4 are intersecting at one point. These two revolute pairs kinematically are equivalent. I can take any one of them. Similarly, these two revolute pairs are kinematically equivalent. They are connecting the same two links and axis is same, so they are kinematically equivalent to one revolute pair. So this is also a 4R mechanism, but not a planar mechanism, because the axis of these 4 revolute pairs are not parallel, and all the points of this mechanism are not moving in parallel planes. So this is what is called a 4R spherical mechanism. All these 4 axes of the revolute pair intersecting at the point O, consequently the distance of any point of this mechanism cannot change from O as the mechanism moves. So all the points lie on the surface of the same sphere. This point always lies on the surface of a sphere. That's why it is called a 4R spherical mechanism. Now we represent the same 4R spherical mechanism or Hooke's joint in this diagram. As you see, this is link number 1 having a revolute pair whose axis is this line. This is the shaft and the fork, which is the same rigid body, represents link number 2, and this cross arm which connects the two forks is link number 3. Link number 2 and 3 has a revolute pair here, and the axis of this revolute pair also passes through this point O. This cross arm C is connected to this fork, which is integral part of this shaft, to this revolute pair, and the axis of this revolute pair between 3 and 4 also passes through the point O. This is link number 1. So this is a Hooke's joint where this angle is 90 degrees and this angle is also 90 degrees and this angle is also 90 degrees. If we consider the two revolute pairs belonging to the same link, that link number 2 has these two revolute pairs here and there, the angle between the axis of these two revolute pairs is 90 degrees. Link number 3 has two revolute pairs, one here and one there, and the angle between the axis of these two revolute pairs is also 90 degrees. Link number 4 has these two revolute pairs, one here and one there, and the angle between the axis of these two revolute pairs is also 90 degrees. So, this Hooke's joint is a special case of a spherical mechanism or spherical linkage where all these angles are 90 degrees. And such a linkage, as I said, is used to transmit power from the propeller shaft which comes out of the gearbox to the input to the differential. And these axes are intersecting. As we see, the input and the output shaft, whichever is input or whichever is output, doesn't matter. These two shaft axes are intersecting at one point. In this diagram, the Hooke's joint is represented by the kinematic diagram. These are the two revolute pairs, axis like this. This is the output shaft and this is the input shaft, and one represents the body of the automobile or the frame or the foundation. What we should note that the angle between these two shaft axes is represented by alpha 4. These two shaft axes which are intersecting at the point O, these two lines lie in a plane, and the angle between these two lines, that is the input shaft and the output shaft, alpha 4, is called the shaft angle. Alpha 4 is called shaft angle. If link number 2, the shaft, rotates about this axis, then link number 4 will rotate about this axis. Let me say I represent the rotation by this. The rotation of shaft 2 I represent by an angle theta 2. That this plane goes down in this direction in theta 2, and this plane goes down in this direction at theta 4. It can be shown that the relationship between theta 4 and theta 2 can be expressed by the expression tan theta 4 will be cosine of the shaft angle alpha 4 into cotangent cot of theta 2. So tan theta 4 is cos alpha 4 into cot theta 2. Theta 2 is measured this way and theta 4 is measured this way. As we see here, the alpha 4 is more than 90 degrees, so cosine alpha 4 is negative. So if cot theta 2 is positive, then tan theta 4 will be negative. That means this will go in the other direction. When the shaft rotates in this configuration, in this direction, this shaft will rotate this way, not the way it is shown here. But this relationship will hold good only if we measure this is the axis of rotation for theta 4 and this is the axis of rotation for theta 2. It is very easy to see by differentiating this expression that the angular velocity of these two shafts will not be same. If I differentiate this, we get sec square theta 4 into theta 4 dot, which if I call omega 4, will be cosine alpha 4, and differentiation of this will give me cosec squared theta 2 into theta 2 dot, which is omega 2. So omega 2 and omega 4 are different depending on the values of theta 4 and theta 2, and obviously the shaft angle alpha 4. So if omega 2 is constant, omega 4 will keep on varying. So even if the input rotates at constant angular velocity, the output will not rotate at constant angular velocity. We can differentiate it once more, assuming omega 2 to be constant, and we can find what will be omega 4 dot. We can differentiate this once more. this expression and get what is alpha 4 even when alpha 4 is there when alpha 2 is 0. Angular acceleration of this shaft may be 0. So it does not transmit a constant angular velocity ratio. It also does not transmit a uniform angular velocity ratio. However, we can use two such Hooke's joints in series to transmit a constant uniform angular velocity ratio. That is called compensating or self-compensating Hooke's joints, which are two Hooke's joints in series, which I will now show you the sketch. This sketch shows a self-compensating Hooke's joint, which is nothing but two identical Hooke's joints in series, having the same shaft angle. Suppose this is the input shaft, which is link number 2, containing this fork. This is the cross arm, and this is the output shaft for this Hooke's joint. One is the frame, 2, 3, 4, and the shaft angle is beta. And this link fork acts as the input shaft for the rest of the mechanism, which again has a cross arm and a fork connected identically, and the shaft angle between this input shaft and this output shaft is same beta. It is same as this shaft angle. In that case, the angular velocity of this shaft will be same as the angular velocity of this shaft. So this is called two Hooke's joints in series which act in a self-compensating manner. However, as we see, this mechanism is cumbersome and takes quite a lot of space. In fact, there is a patent of a compact compensating universal joint which is patented by Bendix Aviation Corporation, which is a different type of mechanism, but which is patented by Bendix Aviation Corporation, which is a very compact self-compensating Hooke's joint. That means it can transmit power between two intersecting shafts using a very compact mechanism. Let me now summarize what we have discussed today. We started our discussion with a simple steering mechanism called Ackermann steering mechanism, which is nothing but a 4R simple planar linkage. Symmetrical linkage such that identical turn can take place for the right hand turn and left hand turn. What we found that because it is simple mechanism, it cannot satisfy the ideal steering requirement for all radius of turning. In fact, we can satisfy the condition of steering only for a particular value of the radius, and we have also shown through an example how to choose the particular value of the radius so that error for all other radius is somewhat less. After that, we discussed what we call a Hooke's joint or a universal joint, which is used again in automobiles to connect two intersecting shafts. This is nothing but a 4R mechanism, but it is a spherical linkage because all the revolute axes are not parallel but rather intersect at one point. Then we showed that in this kind of connection we cannot transmit uniform constant angular velocity ratio. That means if the input shaft rotates at constant speed, the output shaft rotates at variable speed. To compensate this, we can use two such joints, identical joints in series, and get a self-compensating universal joint which can transmit uniform angular velocity ratio between two intersecting shafts. However, that mechanism is not very compact, it becomes quite cumbersome and big, it becomes a 6-link mechanism. However, there exists compact mechanisms to do this, satisfy this, that is to connect two intersecting shafts without having any change of speed from one end to the other, which is being patented by Bendix Aviation Corporation.